So this data set's got a few columns. It's got row number, customer ID, surname. So what we're looking at is a data set of a bank. It's all fictional. It's not a real bank, but it's very realistic. And here we've got a snapshot of if you scroll down to the bottom, there's going to be 10,000 customers. So 10,000 rows in this data set. And what the bank did is they measured some things about these customers. Why did they undergo this whole thing? What's the challenge here? Well, the bank has been using unusual churn result or churn rates. So churn is when people leave the company and they want to understand what the problem is and they want to assess and address that problem. And that's why they've hired you to look into this data set for them and give them some insights and how did this data set come to be? Well, 6 months ago, the bank said there's a big problem. We've got to take a sample of our customers. This is a sample of it. 10,000 is a tiny number for this bank. It has million of customers. It operates, fictional bank operates in Europe in three countries, France, Spain, and Germany, and they have lots and lots of customers. So what they did is they looked this sample of 10,000 customers and they measured 6 months ago everything they knew about them, their ID, surname, credit score, their geography, their agenda, their age, their tenure, so how long they've been with the bank, the balance of the customers at that point in time, the number of products they had at that point in time. So the number of products is things like how many products do they have savings account, do they have a credit card, do they have a loan, the customer have a credit card or not. So there's a yes or no plug. Is the customer an active member? Active member can be measured differently by different organizations. It could be whether or not the customer logged onto their online banking in the past month, whether they did the transaction in the past 2 months, or some other measure like that. And estimated salary, so the bank doesn't know the salary of the customers, but based on the other things that they know, they could estimate the salary for that customer. They give you this information. 6 months ago, they measured all of these things and said, for these 10,000 selected customers, we're going to just watch them. And 6 months down the track, we're going to check who of these customers left and who of those customers stayed. And that's what this column exited represents. It tells you whether or not the person left the bank within this 6 months. So this person over here, sometime within the 6 months, he left the bank, and as of a couple of days ago, he's no longer with the bank. This person is still with the bank. So there's a zero here. Person left the bank, stayed, and so on. So if you see a one, that means the person no longer with the bank, and zero still with the bank. And your goal is to create a demographic centric model to tell the bank which of the customers are at higher risk of leaving. For a lot of customer centric organization, this is going to be values. It's such a value added to any customer centric organization. So whenever an organization deals with customers, this is a lot of value added. And then the other thing is that the skill is going to learn is very transferable. It doesn't have to be for a bank. It doesn't have to be for churn rates. Your demographic segmentation models can be applied to millions of scenarios. So here, for instance, even in a bank, the same scenario could work. Should the person get a loan or not? Should the person be approved for credit or not? And once again, you'd have a binary outcome, uh, whether or not the person is reliable, and you'd build the model and say which people are more likely to be reliable, more likely to default, or that could govern the bank's decision to give loans or not. It could be in fraudulent transactions, and there's a lot of scenarios where you could apply a demographic segmentation model. And it doesn't even have to be your demographic. So whenever you have a scenario, when you have a binary outcome and you have lots of independent variables, you can build a proper, robust model, and that will tell which factors influence the outcome. So you can apply this knowledge. It's good to learn in any kind of scenario. We have a binary outcome and lots of independent variables. Let's start this big implementation of our very first artificial brain. So let's mash this together. We're going to start with the data pre-processing phase, which we will tackle in the same, um, because we quickly want to get the interesting stuff. The first thing we're gonna do is here to import the libraries. We're going to create a new code here, code cell. We're gonna go into our data pre-processing template and get the cell we want, meaning this one, and get back into our implementation, the first cell. So we'll show you this, the beauty of Google Colab. TensorFlow 2.0 is already pre-installed. So the way for to show you this is to first import TensorFlow because it is already pre-installed as a library inside the notebook, but we still need to import it. We actually won't use Matplotlib. We're gonna delete this import in this library and then add a third library here with uh, TensorFlow. And the way to import who is dealt with indeed import, then the name of the library, which is TensorFlow. Then we add a shortcut, simple one like TF. And now we're going to create a new code cell. And inside, we're going to enter the following TF dot double underscore version, double underscore. This will simply print the version of TensorFlow we're using, which indeed TensorFlow to write the brand new TensorFlow. We need to execute the cell on this one. If we execute the cell, this will take some time because the notebook is not running yet. And the way to run this is just click this folder here. Now, it will connect to our runtime to enable file browsing, but start running the notebook. At the same time, let's take the opportunity to upload the data set. Go to your machine learning set code and datasets folder, which had to download either in the previous lectures. Let's go through this section on the artificial neural network. Go to Python and create or select the dataset churn modeling. So you can notice it takes a little bit more time than usual because you know the dataset is this time or more real world and mostly bigger. Let's run the first cell to import libraries. Now let's play this cell to indeed reassure that the TensorFlow version we're going to be working with 0.0, basically TensorFlow 2, which is much more better than the version 1. Let's tackle this part of one data pre-processing. Let's create first and a code cell to import the data set, which we already have in notebook. Let's go to our data pre-processing template and let's copy this second cell to import the data set. Let's go back here and let's paste that inside. The question is, what do we need to replace? The obvious first change we need to do is the name of the data set, which this time is not data.csv, but churn underscore modeling, churn underscore modeling. Let's look at the rows one by one. This line of code creates the matrix features X, and the way it does this is it takes all the columns except the last one. Let's take a look at our data. The first columns are actually irrelevant in the sense that they won't help to predict the outcome of the dependent variable. And these columns are the non-helpful columns are obviously the one. This just gives the row number of this data set. We don't want to include then the customer ID is just a key identifier. Absolutely no impact on the dependent variable. Exited. We will exclude that. We have to the new one that worked, we'll just figure it out, but let's just ease the learning process of our future network. Does the surname have an impact on whether the customer will stay or leave in the blank? Absolutely not. Surname has no impact on the decision of a customer to stay in or leave the bank. We'll also exclude this column, and then all the rest and all other features here are fine. They might have an impact on the dependent variable, meaning they might have helped to predict if customer will stay in the bank or leave the bank. So we will definitely keep all the other ones, meaning all the features starting from this one to credit score. So instead of taking all the columns except the last one, we will take all the columns starting from this one except the last one, meaning all the columns from credit score up to the estimated salary. And the way to do this is still to keep that upper bound of the range, finishing at the one before last column. That's exactly the upper bound, that's the range. But at the left of the range, we won't specify nothing, which means the first goal in the first index, but instead we will specify the index of the column. We want to stop with, which is the credit score. We want to start from here. Therefore, now the question is, what is the index of that column? Indexes start from 0. So this has index 0 then. Therefore, instead of specifying nothing here as a lower bound of the range, we will specify the index 3 so that we can take all the columns starting from the column of index 3 up to the one before last, and taking all the rows, all the values of the data set. And this will create a relevant matrix of features. The next one is fine. It will just take the last column of this data set, which is exactly what we want for our dependent variable, exited. Nothing to change. Just play this cell and we will have our data set, matrix of features, and our dependent variable vector. Let's check it out. Let's create two new code cells. One where we will print the matrix of features X, and one where we will print the dependent variable vector Y. Let's play for this self-print, the matrix of features X, and there we go. We have indeed all the features starting from the credit score. Then the country of residence, the gender, and all the other ones. Has credit card, yes or no, is active, and the last one is the estimated salary. We have all these features perfect. We don't have the dependent variable values because they are right here in Y. These are all the decisions of the customers to stay or leave in the bank. So this one here corresponds to this customer here, which obviously has decided to leave the bank. This actually the same one here, exited one. The second customer has decided to stay in the bank and corresponds to this one, which is exactly this one as well. This customer, first step of the data pre-processing phase, done. And now let's move on to the more advanced steps of our data pre-processing phase, which is encoding the categorical data. There are two category variables. The first one giving the country of residence of the customers, and the second one, the gender. We'll have to do some encoding work here to encode this categorical data in either simple labels, 0 and 1 for the gender, or someone had encoding for these categorical variables in which there is no relationship order between these values, between these categories, France, Spain, and Germany. Start with the label encoding of the gender column, create a new code cell. To do it, we're gonna go into our data pre-processing toolkit and scroll down to find there is no missing data in the data set. We don't have to take care of missing data, so we can directly move to encoding. Since we're taking care of label, encoding, and gender column, we're going to take this. That's exactly the tool we need to perform label encoding. And we will add it inside our notebook. Remember that in our data pre-processing toolkit, we did this on the dependent variable. We want to do it on the specific column of the matrix of features X, and we only need to replace here is the Y by that specific column of the matrix features X to which we want to apply label encoding. Now the question is, how can we get this column? We just need to get the index and then call X with that index. So the first column of X, it hasn't exited. Second column, index 1. This is the third column, which has index 2. Here we simply tend to replace Y by our matrix of features X, of which we're going to take all the rows. Taking them with the column, which means arrange in Python, and then to take the column we want, meaning the gender column, which has index 2. We just need to add here after the comma the index 2. It will take all the rows, but only the column of index 2. We need to take this and paste that inside the fit transform method called from our object, which is an instance of the label encoder class, and then we just perform label encoding to the gender. So let's make sure, let's create a new cell and print the matrix of features X, run. And now let's print X. Make sure that we no longer see female, 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 male, female, but encoding there will be 1 for female or 0 for female and 0 for male or 1 for male. So that's the new column after the label encoding. So female was encoded 0 and male was 1. A random decision of the machine to choose the integers. Now this column is label encoded. Now we're going to proceed to the one-hot encoding of the geography column. And this time we have indeed to perform one-hot encoding between there and encode France into 0, then Spain into 1, and Spain 1, and Germany into 3. Again, take the cell in the toolkit and paste here inside the new code cell to one-hot encode the geography column. What we have to replace in that cell, the only thing that you have to change inside the cell is that index of the column you want to apply one-hot encoding. In our data set, which fell of our or the category called variable with the 3 different states was in the first column. That's why we had index 0 here. This column is actually the second column. It has index 1, very simple. Replace 0 here by 1. That's it. The rest will be done automatically. Let's play that cell. Create a new code cell to print again X. And now let's play that cell and see what X has become. And remember, when we perform one-hot encoding, well, the dummy variables are actually moved to the first columns of the matrix features. We have them exactly here in the 3 first columns. So let's see how the one-hot encoding was done. This is the first combination of dummy variables, which corresponds to France. These are the same rows here. Therefore, France was encoded into 100. Spain was encoded in 2001, and Germany was encoded into this 1010. So that's our one hat coding. Then we no longer see the gender column, but nor it is still there, still here. One hat coding was not only done successfully, but we went on went on efficiently. Now let's move to the next step, which is to split the data set into the training set and test set. We're gonna do that. So going back to the template, we have to get this cell that splits the data set into training set and test set. Paste that back into our implementation in a new code cell right here, and then we can just paste. We will just play that cell. We don't have to do a print of these four entities. Um, you're free to do any modification. And finally, we have a final step of our phase, which is feature scaling. Uh, I want, or the feature scaling is compulsory for deep learning. Whenever you build an artificial neural network, you have to apply features. That's absolutely fundamental. And it is so fundamental that we will actually apply feature scaling to all our features, regardless of whether they already have some values of 0 and 1, like the dummy variables. Uh, the feature scaling step here will be very simple. We'll just take our data pre-processing toolkit. We'll go right at the end because this is our last tool. We'll take that full cell and we will paste it right back just below feature scaling. We'll paste it here, and now instead of selecting some specific index here, we'll just take everything. So removing all our index selections here so that we can just scale everything. That's the way it should be for neural network, for building and training a neural network. This will just apply feature scaling to all the features of both the training set and the test set. Our feature or our scale object is only fitted to the training set. It's to avoid information leak or leakage. So let's run this final cell, and then the phase will be over, or the feature scaling or the data pre-processing. Data pre-processing phase for 70% of the work of a data scientist. That's why it was really important for me to give you some very efficient data pre-processing template. In less than 20 minutes, but without the, but because of our pre-processing toolkit template, we have it here and we've done it in just less than 20 minutes. So let's continue our implementation to build the artificial neural network. We will do it in 4 steps. The first step will initialize the ANN as a sequence of layers. Then we'll add the input layer, the first hidden layer composed of a certain number of neurons, which we'll choose together. Then we'll add the second hidden layer in order to build indeed a deep learning model as opposed to a shallow learning model. And then finally, we will add the output layer, which will contain what we want to predict. We're going to tackle these 4 steps in this one same lecture, starting with this one, initializing the ANN as a sequence of layers. Create a new code cell. First thing we have to do is to create a variable that will be nothing else than the artificial neural network itself. This ANN will be created as an object of a certain class. And that certain class is is the sequential class, which allows exactly to build an artificial neural network, but as a sequence of layers as opposed to a computational graph. It's actually a sequence of layers starting from the input layer, and then successively we have the fully connected layer up to the final output layer. And then the other type of new network is computational graph. Uh, Neurons connected not in successive layers. Example is in Boltzmann machine. They are example of computational graph. They're not covered in this um, lecture, but we will cover or it or uh, we'll just get the right introduction to deep learning, and then so going back, we create this ANN will be nothing else than the ANN network we're going to build, and we will create that variable as an object of a sequential class. The sequential class is not taken from nowhere. It's actually taken from the models module from the Keras library, which since TensorFlow 2.0 belongs to. Since the new TensorFlow, the new version 2.0, Keras was integrated into TensorFlow. The way to call the sequential class here is to go first TensorFlow, which has a short TF from which we're going to call a Keras library, and from the models module, from which we call indeed that sequential class. And so that creates this AN variable, which represents our ANN created as an instance of that sequential class, which initializes or our ANN as a sequential of layers. That's the first step. Next is to add the input layer and the first hidden layer. We're going to start using the famous class in TensorFlow and even in PyTorch, which is another great library. The way to add a fully connected layer into an ANN will, whatever phase you are, whatever the state of your ANN is, to use the class. The way we use it is very simple, taking our ANN network object in that instance of the special class. So that's the method we need right now to add anything we want. It is a hidden layer or a dropout layer, which allows to prevent overfitting. We will see layer, which is a convolutional layer. We'll see later in the next topics. And then the way to add this is to enter this parenthesis, add, or add is the method, add exactly that fully connected layer. And the new class is the dense class. So the fully connected layer will be created as an object of the dense class, and therefore we have to do is to call the dense class. We'll create that fully connected layer. At the same time, it will automatically add the input layer. So let's go to the dense class. The dense is not taken from nowhere. It belongs to a certain path of libraries. The root of that library is our TensorFlow or our TensorFlow library, from which we're going to call once again the Keras library. This time we're not going to call the module. This is the module that contains the different tools, and by tools, the classes, we mean the classes. That's from this layer as module that we're going to call Arden's class, which as any class can take several arguments in here. We have to enter these arguments. The important one is this one unit, which corresponds exactly to the number of neurons, the number of hidden neurons. We want to have in this first hidden layer, we will automatically have our different features. In the input layer, or the input neurons, that will be one neuron, another input neuron, up to this one. All this will be the input neurons. We will create that first hidden layer. We'll have some hidden neurons inside. In this dense function, you can specify how many hidden neurons you want to have. And how do we know how many neurons we want? Is there a rule of thumb, or should we just experiment? Unfortunately, there is no rule of thumb. It is just based on experimentation, or we call it the work of an artist. We have to experiment with different hyperparameters. We call them hyperparameters in the sense that these are parameters that won't be trained during the training process. There is no rule of thumb. We just have to pick one number here. We wouldn't sound irrelevant or extravagant, and that number will be 6. We tried several numbers and more or less the same accuracy in the end. But 6 is totally fine. Here inside this dense class, we'll enter our first parameter, which is unit. Units equals 6. And now the next is, you can see many of them. We'll keep the default value for all of them except this one, which corresponds to the activation function. The intuition lectures, the activation function is the hidden layer. In the hidden layers of a fully connected network must be the rectifier activation function. So here we have to specify that we want to rectify the rectify activation function. We have to enter here our activation parameter, the code name for the rectifier, which is in quotes, well, ReLU. That's the code name for the rectifier activation function. This is all you have to enter, and fully working first, fully connected hidden layer. Now, you know how to build now a shallow neural network, and you know a second, or in a second, we will build a deep neural network. The only thing that you have to do is just copy this line of code, and then a new line of code here for the second here. In there, you just need to paste here. So this add method can add any new layer at whatever stage of the process. You can use this add method to add anything, and the weight add a second hidden layer. 6 million neurons in the first layer and 6 other ones in the second hidden layer is just fine. Now add the output layer. You have to do something special, something different than what we did here. Let's create a new code cell and base and paste what we just copied before. Once again, this time we'll have to change two things which correspond actually to the values of these two parameters. First, why they are the same? Because we're adding a new layer. Here we're still using the add method to add this final output layer. We want our output layer to be fully connected, so that second layer, we're using again the dense class. Then these two parameters have to be changed. So we have to change this value according, or 6 has to be replaced by we need to have a look at our dependent variable again, which is this one. The output contains the dimensions of the output you want to predict. Since we actually want to predict a binary variable which can take the value 1 or 0, the dimension is actually 1 because we only need one neuron to get that final prediction 0, 1. However, if we were doing classification with a non-binary dependent variable, like dependent variable that has three classes, let's say A, B, C, we would actually need three dimensions, three output neurons, two, once again, one hot code, that dependent variable because there's no relationship order of the classes. A, for example, would have encoded 00, B would have 010, and C would be 001, and you need three neurons getting this value 0 and 1 to encode your three classes. But here, since we have binary, we only need one neuron to encode these outcomes into 1 or 0, and therefore with the value of that unit parameter here that we have to replace right now is actually 1. One output neuron encoding the dependent variable, and then second change corresponds of course to that activation function and to the value of the activation function, the activation function of the output layer. Here is a sigmoid activation because having a sigmoid allows to get not only ultimate predictions but even better. It will give you the probabilities that the binary outcome is 1. So that we will not only get the predictions of whether the customer choose to leave or not the bank, but we will also have for each customer the probability that the customer leaves the bank. But all this thanks to the sigmoid activation function. You want that sigmoid for the output layer only. All the layers, the other fully connected layers will get the ReLU activation function. And now uh, we're actually done with the creation of this very first ANN. Was that hard? Was that overwhelming? I don't think so, and that is the beauty of TensorFlow 2.0. I hope you enjoyed this. We will go to the next topic, which is training on the data set next. That's what we're gonna do, and then we're going to make it our brain, that what we just implemented here, smarter by training the ANN. Then our ANN on the whole training set in a certain number of epochs, and you will see that training process and we'll visualize it. So here is the second half of creating ANN, which is to train on the whole training set. The first one is to compile the ANN with an optimizer loss function and a metric which will be the accuracy because we're doing some classification. And then the second step will be to train the ANN on the training set over a certain number of epochs. So starting with the first step, compile the ANN. Doing this will be super simple thanks to TensorFlow library that integrated Keras. Indeed, it compile our ANN, and we first need to start from our end object. And then from this object, we're going to call a new method, which this time, of course, won't be the add method, but the method to compile an ANN is simply the compile method, as simple as that. We didn't even have to look at the TensorFlow documentation. Next, what do we have to enter as parameter inside this compile method? We have to enter three parameters. The first one is the optimizer. The second is the loss. And the third one is the matrix with an X parameter. You can actually choose several metrics to evaluate your ANN at the same time, but we'll choose one and we'll choose accuracy. These are the three parameters. Let's start with the first one up to the optimizer equals. Come to the next one is the loss for the loss function. The third one is the matrix parameter. So for the optimizer, which one would you like to get? Into intuition, we mentioned that the best one are the optimizers that can perform the gradient descent. And the best of them, the one that we recommend is the Atom optimizer, which is very performance optimizer that can perform stochastic gradient descent. It is what we will update the weights in order to reduce the loss error between your predictions and the real results. Then, when we train in on the training set, we will at each iteration compare the predictions in a batch to the real results in the same batch. And that optimizer here will update the weights through stochastic gradient descent because we're going to choose Adam optimizer to add the next iteration, hopefully reduce the loss. That's here the loss function, then the accuracy, that's our final evaluation. We're going to choose the Adam optimizer and the code name for that is simply but no capital letter Adam. Now you an artificial neural network with an optimizer. Then we also have to combine it with a loss function. When we are doing binary, the loss function must always be the following. One entered in quotes, of course, which is binary underscore cross entropy, just like that. And now, let me tell you what you would have to enter if you're doing non-binary. For example, three different categories, prediction. You have to enter categorical cross entropy loss. For binary, the loss must be binary cross entropy. For non-binary, the loss must be categorical. Cross entropy, and then take this, remember that for regression, we can also do artificial neural networks for regression. We have this, or we already discuss it in the previous lecture to show you the result of the regression. So let's enter the final matrix. We can actually choose several matrix. In order to enter the values of this parameter, we have to enter them in a pair of square brackets. The list of the different metrics with which you want to evaluate your ANN during the training, but we will only choose the main one, the most essential one, which is the accuracy in which you have to enter in quotes. Accuracy, just like the classic spelling. Now you know how to do a full compile of your ANN with an optimizer, a loss, and some matrix. Perfect. Let's move to the next step, meaning the step where we will train the ANN onto the whole training set. Let's create a new code cell, and now according or how do we need to start this training? Well, once again, it's always the same thing. We need to take our ANN object, then call a new method which will perform the training, and then enter a couple of parameters. Let's start with ANN dot, and then according or what method that can train. The method to train whatever learning model is always the same one. This is the fit method, in which will take always the same parameters. The first one is xtrain for the matrix of features of the training set, then the ytrain for the dependent variable vector of the training set. And then when training an artificial neural network, we actually to enter two more parameters, which are first batch size, because batch learning is always more efficient and more performant when training in ANN. Instead of comparing a prediction to the real result one by one to compute and reduce the loss, you're going to do that with several predictions compared to several real results into a batch. And the batch size here, the batch size parameter gives exactly the number of predictions you want to have in the batch to be compared to the same number of real results. And the classic value of the batch size is actually 32. If you don't want to spend too much time tuning this hyperparameter, I recommend to choose the default value, 32. But anyway, hyperparameter here, uh, it's is also important. So batch size equals 32. The number of epochs next. A neural network has to be trained over a certain amount of epochs. So as to improve the accuracy over time, we will clearly see that once we execute the cell, the name of the parameter for the number of epochs is simply epochs. And while you will see that it will go very fast, you can just take 100 there. And feel free to choose another number as long as it is not too small, because your network needs a certain amount of epochs in order to learn properly, learn the correlations to get the ultimate best predictions. So done with point 3 now. We will execute all the cells. This was the last cell of the data pre-processing phase. It was run properly. Let's run each cell one by one and see what we're gonna get in the end during the training. Let's go with this one. Initializing the ANN. Next, adding the input layer and first hidden layer. Next is adding the second hidden layer. Now this one adding the output layer. And part 3, executing first the cell compiling the ANN. We're about to train the ANN on the training set over 100 epochs. And here we go. The training is starting. It's going pretty fast. Look at the accuracy and how it is evolving over the box, and we can see that it is actually increasing very fast. And mostly we see that it is actually converging. In 86, at about the 20th, we actually didn't need that 100 box, 100, but 20 was fine. But anyway, it's going fast and it's very over soon. The training was done in more or less 20 seconds, and the final accuracy we get on the training set, we'll have to check the same on the test set, is averaging around 4.86. That means out of 100, you have 86 correct predictions. So you made a very good deep learning model. You can be proud, or um, you can take this part 4, and in our next video, uh, or in the next part, we will predict the customer will stay or leave the bank. You can try it before proceeding to the next step. Um, You can try to use ANN to predict if the customer with the following information will leave the bank, yes or no. And following information or that it is a French customer, for example, with a credit score of 600 male, is for or had been in the bank for 3 years, has $60,000 in account, and so on. You can figure it out before proceeding to the next step. So we're making the predictions and evaluating the model, and um, we if you tried it before proceeding in this section, I hope you did try, but now we will implement it together. So this code cell here, we left this to enter the solution, but this is just too common. Let's just remove it. And now, how do we complete this homework? We need to get first our aid and model from which we're gonna call a new method. No different than the add method or the fit method. We need to call the predict method. We call this predict method to predict if yes, no, the customer with the following information will leave the bank. And now, since this is a method, I'm going to add sample in it. Parenthesis here. Let's scroll down. We have all the information to predict method, but this is given in the instructions of the, or we have to enter these informations, but there are a few things to pay attention to. There are actually three things. That's why we wanted to give you this homework. I wanted to see if you could pay attention to three important things to include inside that the predict method. Let's start with the most essential one, which is the double pair of square brackets. It's important to remember that any input of the predict method must be to the array, whether it is the test set to predict, and in symbol of outcomes, symbol of observations, or whether it is a single prediction. Anything has to be in a double pair of square brackets, which therefore makes a 2D array. The format expected by the predict method is always 2D array. That was the first thing. Then inside this array, we're going to enter different informations here. And the second important thing is about uh, geography, France. Do we have to enter the dispersed information here for the geography variable? Do we have to enter the string France, or do we have to enter something else? Of course, we have to enter something else, and that is are the values of the dummy variable. That's the second thing you had to do correctly. And therefore, now we need to check what was the encoding for France. We'll remember if we have to look at our matrix of features X right above in part 1, uh, it will be pricing. This is the matrix of features X, the whole matrix containing all the customers. So in order to know what France corresponds to terms of encoding, we have to have a look at the first observation before one hot encoding was applied, because indeed the was first observation corresponds to France. And so now we just need to compare France here to the one half including or encoding resulting from what we did here. And we can see that the first row here contains 100 as the values of the dummy variables, and therefore France was encoded indeed into 100. So the dummy variable values for the France country and the geography variable is indeed 100. That's exactly what we have to enter here as the first parameter. Let's enter 100. There you go. That enters that first value of the first parameter, geography. And then all the rest is easy for the credit score. We will enter 600. Then let's see the gender male. Remember, male was encoded as 1 and female was encoded at 0. Here, in order to enter the male gender, we need to enter 1, then 40 years old. Very simply, we enter 40, then tenure, 3 years, we enter 3 here. Then balance $60,000, so we enter 60,000. Then let's see number of products. 2, does this customer have a credit card? Yes. So 1, because 1 corresponds to yes and 0 corresponds to no. Is this customer an active member? Yes. So 1 again as estimated salary. Finally, $50,000. Our last parameter value is $50,000. Yes, okay, good. And now I have a question for you. Do you think we're done with this prediction using the predict method with all these informations? The answer is no. And that leads to the third thing you had to pay attention to, which is the fact that remember, to predict method should be called and on which the same scaling was applied as in the training. Since we trained our artificial neural network with the scaled values, the scaled values of the features, the predict method has to be called on to these observations to which the same scaling was applied. And that was the third thing you must have not forgotten, which is the fact that you have to apply your SC object here to scale that single observation. That's super important. Make sure to pay attention to this. Check if some scaling was applied during the training. And it is the case here. Anyway, it is always the case for neural networks. And therefore, in the predict method, we will need to scale that single observation. And the way to do this is calling our SC object. This one from which we're going to go, be careful not to fit transform because the fit transform is used to remember, get the mean, and standard deviation of the values and training set in order to fit your scalar to the training set. But then for the test set, we only need to call transform method because if we fitted again the scalar, that would cause some information leakage. Um, Remember that on the test set or on new observations in which you deploy your model in production, you can only apply the transform method. And that's what we're going to call here transform, which has to take as input the whole observation in this double pair of square brackets. So basically, that's it. We can run that cell, we can get our prediction, and remember that when compiling an optimizer, a loss function, and a matrix, remember that in the output of our ANN, we choose a sigmoid activation function, which therefore will return this prediction in the form of a probability, meaning that instead of getting the final outcome, 1 or 0, whether the customer left or stayed in the bank, while we're going to get the probability that this customer leaves the bank, you'll see it will be very easy to get the final prediction 1 or 0. But first, let us show you what we get with this prediction. We're going to put all this into a print, all this into a third pair of parentheses. Let me play that cell and get that the predicted probability that this customer leaves the bank is all 0.04, 0.0380, 0.04, and therefore it is predicted that this customer has a very low chance to leave the bank. And if you don't want the outcome in the form of a probability, the trick is to convert this into the final prediction. You just need to, just before the last parenthesis, the larger symbol, and then both point 0.5. Why is that? Because all this and the predict uh, all the information is of the customers up to here returns exactly the predicted probability. We choose a threshold of open 5 to say that if that predicted probability is larger than 5, well, we will consider the final result to be 1, right? Because the predicted probability that the outcome is 1 is larger than open 5, meaning that there is more than 50% chance that the predicted outcome is 1. So we'll consider it to be 1. And however, if the predicted probability that the customer leaves the bank is below zero point 0.5, we will consider it to be 0. You can choose a different value of the threshold, especially when you have critical outcome for a critical decision. And in that case, you can, for example, increase the threshold. But here, let's just be the default value, zero point 0.5. This totally makes sense for our case study. And therefore, now if we are to execute this cell, we will of course get the final outcome, which will be of course 0 or false. False, we should not say goodbye to that customer, or false, the customer won't leave the bank. In other words, it will stay in the bank. But anyway, we just wanted to show you how to use your ANN to predict the outcome of a single observation, meaning a single customer. Remember three things. First, you have to enter your information in a 2D array with a double pair of square brackets. Then you need to be careful with the dummy variable values. Here, instead of entering the string input for that category call variable. And then the third thing, remember to apply scaling from the EC object because your ANN was trained with scaled values. So now, finish the implementation. The last two cells we have, by the way, um, we have some notes so that you can remember. We have two cells. The first one is that cell which very well where we predict the test that results by displaying next to each other the vector of predictions, widespread, and a vector of real results, y-test. So we're going to do this most efficiently by juggling with our toolkits. Finally, we will make the confusion matrix to get the final accuracy of the test set. So let's do this. We're going to go back into our machine learning. So let's click the shortcut here to get the original base of the folder machine learning A to Z. Then we're gonna go into part 3 classification to take any more or logistic regression, for example, that Python. Then open this implementation, which contains indeed a lot of tools you can do with classification. Doing right now with our NN, and now we're just going to scroll down, and the final cell, which will do exactly what we're about to do with our uh, or to display next to each other the vector of predictions and the vector of real results. So that cell, let's paste that inside the new code cell right here. Remember that now, since our classifier, which is no longer called classifier but ANN, returns the prediction in the form of probabilities, we just have to do a little something here, which is to convert our predicted probabilities, which are in spread, into predicted binary outcome 0 or 1. And the trick to do that is exactly the same as the trick we used here. It is to update ypred the following way by setting it equal to the Boolean result of whether y, or the result of whether y press. The predicted probability is larger than 4.5, so that if y spread is between 0 and zero point 0.5, then this new y print will become 0 because this won't be true. And if y pred is larger than open or zero point 0.5, then this will be true. Therefore, y pred will be equal to 1. Then we'll get therefore the final predicted binary outcome 0 or 1, and then the rest is the same. Let's play that cell get indeed displayed next to each other. First on the left, the vector of predictions y pred, and on the right of the real results. Now we don't have all the results observations. We can already see that the predictions look pretty good. The first customer of the test set, that's all the customers of the test set. That first customer in reality stayed in the bank and was predicted to stay in the bank. However, the second customer actually left. In reality, the bank uh, but predicted not to was predicted to stay in the bank. Then the third customer stayed in reality in the bank and predicted to stay in the bank as well. And then for these three last customers of the test set, they in reality stayed in the bank and were predicted to stay indeed in the bank. So the results look really good, but the real way to check this is with our confusion matrix. And therefore here in our logistic regression tool, the code template, we just have to scroll down a little bit more to find the code of the confusion matrix and also the computation of the accuracy. Let's just get this, then copy that into a new code cell, then paste. And now you are ready to get the final accuracy of your very first ANN on the test set, meaning on new customer on which the model wasn't trained. So let's check this out. Let's play that cell and we get an accuracy over 86%. That's really good because it means that out of 100 customers, 86 were predicted correctly to either stay in or leave the bank. And we can actually see here the details of these predictions. We had 1,520 correct predictions that the customer stays in the bank. Then we had 203 correct predictions that the customer leaves the bank. Then we have 75 incorrect predictions that the customer leaves the bank, and 202 incorrect predictions that the customer stays in the bank. So that looks pretty good. Accuracy of 86% is a very decent accuracy. Of course, uh, we challenge you to at least get 1 or 2 extra% of accuracy, but actually we experiment, it will be very hard to beat this. So don't waste too much time on this.